Hi everybody and welcome to another part of the Solidity tutorials. In this part we're going to correct our previous binding curve that solve a smart contract, because this is not the correct way of writing this contract, right? I don't mean that there is a problem inside of the code, or I don't even mean that there is any problem with a small part of it, but the problem is with the algorithm that we're writing it, right? So let me explain how it has gone on and what we're going to do in order to correct it. So first of all, what's wrong with this smart contract? Well, the problem is that, for example, here we want to buy 100 tokens, and the price of the 100 tokens are the same, right? So it doesn't exactly follow the curve. So for it's some kind of a discrete or actually discrete kind of curve, not a continuous one, right? So what I mean by that is that, for example, the actual price model should go in a way that, for example, you buy the first token, it's $1, for example, the next one should be more than $1. It should follow the curve, not that all of the tokens are $1, right? So in the classical markets, this smart contract that we previously wrote, it just follows the classical market, the market that we're buying and selling stuff, and the prices are constant. They don't go up and down based on the number of requests, based on the number of sales, right? So this one follows the bonding curve in a much more accurate way, the one that we're going to write, and it is because that it's going to follow the curve exactly based on the number of minting the tokens or the supply. So which means that, for example, I want to buy 100 tokens. The first one has a kind of a price, but um, the token number 2 that I want to buy is more, and how much more, it is based on the formula that we write in the get current price, right? So if you want to calculate the price of all of the 100 tokens, you should use the integral formula, which means that, for example, if it's a multiplied by supply to the power of 2 plus b, you should then integrate this formula, and it will be a kind of a power to the power of 3 kind of formula, which we're going to first calculate the integral of this formula, and then we'll write it and then calculate the entire price of the number of tokens, and then that is going to be a corrected way our bonding curve.solve works. So first of all, I wrote this smart contract to show you how our markets actually work out there, but how it should be. Actually, it would be like this. So now we're going to write our new smart contract based on this modification that I've just told you, and we're going to see how our smart contract changes. So now in the contracts folder, I will create another smart contract, so new file, and I'm going to name it correct. So correct with dollar, correct bonding curve.solve. Now that we've got it created, let's copy and paste the first 2 lines, actually the first 3 lines, because we're going to need the open zip link. And here we go. So now I'm going to create another contract, and here I can say contract correct bonding curve. So this is actually not the correct bonding curve too, because here I'm not going to use integral, right? Here I said that we have this formula, it's better to integrate it, and yes, that's good, but here we're going to do exactly the same as what I'm going to do with integral, but here with the for loop. But for loop is not programmatically correct way. So now let's create our contract, and instead of the contracts folder, I'm going to write bonding curve dot sol 2, or bonding curve actually 2, bonding curve 2 dot sol, and still this one is not the final version of the bonding curve dot sol, because in this part I'm not going to use integral. I'm going to use the for loop to be a kind of more programmatic kind of algorithm. But if you use integral, it becomes much easier for the smart contract to be processed, right? So it makes the entire process much easier once you use integral. But if you use the for loop, then the for loop has to continue for 100 times in order to calculate the entire price based on the current price. And so I will explain instead of this smart contract what's going to happen. But notice that there is also another bonding curve which we're going to write after this one, and that is going to use integral, not this one. So first of all, just as always, let's copy and paste the first 3 lines. So here we go. So contract and bonding curve two, or 2 like this, and then don't forget about is ERC20 because we're going to use the OpenZeppelin ERC20.sol. So let's open the brackets. Now the first thing first, let's define the constants. So A is 1, B is 100, so B is the fixed amount, A is the coefficient. So uint 256 public constant A equals 1, and uint 256 public constant B equals to 100. Here we go. And then uint 256 public supply, uint 256 public supply. Here we go. And then we've got the mapping. So most of the smart contract is nearly the same as what we had instead of the previous one. So we have some of the same variables, mappings, and so on. So the mapping from the address to the uint 256 public balances. So this mapping is for the balances of the addresses. So address to the uint 256 public balances, and then we've got a constructor here, string memory. It gets the string memory name, also a string memory symbol, and you might guess what it is. This is the token specifications that we enter before deploying the contract, and we determine what kind of the token it is, with what name and what symbol. So here it is ERC20 and ERC20 and name and symbol. So name and symbol. Notice that you can also add the total supply and other variables, but here the total supply is what is under our control, right? So we want to increase the total supply by minting or burning the tokens, and also using the total supply we're going to determine the price. So here let's open up and close the brackets. Here we go for the constructor. So now the first thing is to write the function by token. Function by tokens. So it will get the uint 256 token amount. Oh, it should like this, and that's it. So it's public payable kind of a function, open the bracket, and then here we'll determine the ETH amount, uint 256 ETH amount, and now we're going to calculate ETH amount. This is a function that we will write later, so it will get the token amount and true, and I will tell you what true is. So I don't think we had this in the previous contract. Let me check. If we had it, then you have no problem, but no, we didn't have this one. So I will explain what this is, but for now let's write it. I will say why we're writing it. So calculate ETH amount, token amount, and there's this status which is either true or false, and then it will require that the message.value require that the msg.value be greater than or equal to the ETH amount. Otherwise it will tell the user insufficient funds. Here we go, and then this is the requirement, and then we will mint the tokens. So based on the number of tokens there are, we will determine the mint tokens according to the number of tokens. So msg.sender is the person who's going to get the tokens, and the token amount is what we got here in the second property. So after minting them, we'll have the balances of the msg.sender plus equal the token amount. So that's how we increase the number of, actually the balance of the holder, the person who is going to buy the tokens. So we'll continue the rest of the smart contract in the next video. So till the next one, goodbye.